All right, so we're back here, going over the contains method. So we finished writing up the contains method, and we found that basically that what we're trying to do is that we're searching for this item in the tree. We're asking, we're just asking basically, does the subtree that that has root as its root contain this item? So we ask that question, and we find that basically if the root is null, well, if the tree is empty or the subtree is empty, then we're going to return false because we couldn't find it. Otherwise, we're going to use the compare to function to compare the item to what's actually in the tree or what's in the root. That will let us know, and since everything in the tree is ordered, if we get a less than symbol, if we get a negative comparison result, that means that we want to go to the left of the tree. That means because the item we're looking for is smaller than the item in the root. If we got back a larger result, we're going to go to the right because that means the item we're looking for is larger than the root. And finally, if we got a 0 back, that meant they're completely equal, so we return true. That meant we found the result we're looking for. Now, what's great is that we can use this for this basic equation for add and for the add method and for the remove method. One thing we can do also, just to optimize this bit a little bit, or to make this a bit cleaner, is we can remove the else statement over here because it's kind of unnecessary. Because it's either going to be, because root's either going to be null or it's going to exist, and if it exists, the item we're looking for is either going to be less than the item, equal to the item, or greater than the item. So now let's go ahead and ask, how do we do the add method? All right, so the add method, we're going to use, again, we're going to use a private wrapper method, and this is going to look like this. Sorry, a private recursive method with the public wrapper method. It's going to look like this. Public node E, and so we're returning a node, add, node E. Root E item. So let's go over what this is going to, and I'm just going to put return null for a second. Return null. What we're going to do is we're going to go over what each of these items represent, or what each of these parameters in the return value represents. This, of course, says we want to add this item. What are we adding it to? Well, just like we were checking if item existed in the root of this subtree, sorry, in the tree with root as the root of that subtree, we're asking if we're going to try to add this item to the tree that has root as its root, or rather, this node, which we call root, as its root. And so what are we returning here? Well, what we're going to return is a node, and we're going to return that to our parent, telling them to make this your child. Now, this seems a bit weird. It's kind of unnecessary for add, but the reason I do this is that it makes it symmetric with the remove method when we do that, because the remove method is going to do the same thing, because when we remove something, we're going to tell, basically what we're going to say is change this to be your child, because we're removing this item. So this helps keep it a bit less complicated when we go to remove method. It reduces the if we can figure out what's going on here. But everything else basically works pretty much the same as the contains method. In fact, we can copy most of that over, but I'll go ahead and type it out because that's probably what you're going to be doing. So if root equals null. So say we're trying to add this, whoops, in the wrong, it should probably be in the right thing. So if root equals null. So in other words, if we can't find this, if we're adding to this tree and this tree is empty, well, that means we should probably create a new tree with this item as the new root. So new node item. There we go. And I'll give you the first bit of how this works over here. This dot root equals add this dot root so now how will this interact? We'll say we're adding our first item to the list. If we add this first item to the list, we'll say add it to the root of the entire tree. And since we're adding the very first thing, the root will be null, and we're saying return a new node containing that item, and we're going to make that the root. Essentially, we're telling the person who called us, which is either this function up here or our parent node, to make this your child. Okay, so the other big thing about how is add going to work, right? I believe I described it before, but let's make sure we understand how add works, right? We're not going to try to rebalance the tree or anything as we're adding nodes, because that gets way too complicated. In fact, often what we'll do, even with self-balancing trees, what you're going to do is you're going to add nodes in this very same way and then rebalance it afterwards. So what we're going to do is we want to make adding as easy as possible. So we're going to basically look for the first appropriate spot that we can put this item such that the tree remains sorted. And in that case, that means, so once we find the first appropriate spot where this tree remains sorted, we will go ahead and put that node there. So let's go ahead, and I feel like I have to paint this, so draw this, but I don't have a whiteboard. So might as well show you my terrible MS Paint skills. I mean, why not? I've embarrassed myself in many other ways in front of you guys. So let's go ahead and hope I remember how to do stuff. So let's go ahead and make our root 5. We've got 2 over here as our node. Yep, terrible MS Paint skills for the win. 7 over here. So how would we add the value 6 to this tree? Well, we'd start at the root. We'd start at the root over here, and we'd ask, hey, is 6 equal to, greater than, or less than, how does 6 compare to 5? Well, 6 is greater than 5, so if 6 is going to fit into this tree, it needs to go to the right of the tree, to 7. So now we just repeat asking the question, how does 6 compare to 7? Well, it's less than 7, so it needs to go to the left. Oh, there's an empty spot there. So we'll go ahead and put 6 in the empty spot over there as 7's left child. Okay, how do I want to add something like, let's say, I don't know, 3 to the tree? Well, 3 is less than 5, that's greater than 2, so we're going to go ahead and put 3 over here. Again, my terrible, oh, there's a Control Z button for a reason. Woohoo, terrible MS Paint skills, right? But you just improvise. Okay, so goes left, then right, that was the first open space, and say we added 4 to this tree now. So now we're adding 4. 5, 4 is less than 5, 4 is greater than 2, 4 is greater than 3, so it would go over here. All right, so your tuition dollars at work, Skulk. So let's go ahead and move on to see. So everybody understands how we're adding now. So okay, so this was representing us getting the empty spot. And this is telling the person who called us, hey, attach this node to be your child. Which child? Well, you'll figure that you'll know which child because you're going to be saying add this to my left subtree or add this to my right subtree. So we're just going to follow the same thing we did over here. We're going to first do a comparison result. Int comparison result is equal to item.compare to root.item. Okay, we'll remove this return null at the end because it's going to be unnecessary. So we check, is the item less than, greater than, or equal to? Which brings us to one more question. Say I'm adding the node 5 to this tree. Say I want to add 5, okay? How should I handle that? I believe the book handles that by saying just throw out 5. Just throw it out. Don't need it. Okay. I think that's a bit of a cheap solution, unnecessary, but it is a solution. If you get an equal sign, you can just say, we're not going to do anything. Okay. So what should I do over here? Otherwise, what if I don't want to throw it out? Well, I'll use the term of maybe that if I'm adding if it's equal to, it's going to go to the left. So anything, if it's less than, it's going to go to the left just like an equal to. Okay. That way we can have duplicates in the tree. So 5 would go over here, where it would be greater than 2, 3, and 4, and then it'd end up as a child of 4. This can make things a bit complicated for deletion operations, but whatever. So, so let's say if comparison result is less than or equal to in this case, well, we can make them separate cases though, just to make sure. Let's keep them separate cases actually, just to keep it symmetric with everything else. Else, if comparison result is less than 0, else, if it's not equal to, and it's not less than, it's got to be greater than. So we'll leave this blank. You can fill that in however you like. You can fill it in the same way I'm going to, or you can do, or you can actually leave this blank and say, we're good, return null. So what should we do over here? Well, if comparison result is less than 0, what are we going to do? Well, that means we want to add it to our left subtree. So we will say, so we need to call, and so let's go ahead and say add. So you know what the recursive call is, right? You want to add this to root.left. But this is returning a node, right? What if root.left is null? It's going to return this node. So in that case, I'll want to do, so this is where I say it gets a bit clever. Root.left is equal to the result of adding this item to root.left. If it's null, it's going to be this new node. And if it's not null, what is it going to be? Well, just for me, since I return a node over here, I'm going to return root. Basically what goes on over here. I'm going to basically tell this, tell my left child, hey, add this item to your subtree, okay? And then if what is my left child changes, then set it up to be this thing. And that's great for when we actually do anything that has to deal with rebalancing, but which we're not going to get into. And then what about this return statement? Well, here I'm telling my parent, hey, just so you know, I'm still here, right? Because you probably did this root.left or root.right call on me. I'm still here. I'm still your left or right child. So I just wanted to let you know I haven't changed, right? And so if I'm the caller and I get that back, I'll set this to root.left, and I'll go through that on bad MS Paint one to show you how that works. Okay. And again, this becomes very easy with this method because we're just going to be doing this, the same way. Add, if it's greater than, add it to the right subtree, and then return myself again. We'll just simply copy this over here, and the return null is now unnecessary. All right, and again, you can fill this out however you want. You can say return null if you want to over there. So how is this working? Well, this says, let's see, select, delete. So this says, brush. This says if we've got this node over here, say 5, right? Okay. Let's go ahead and add another node to this tree. Let's add 3 to this tree. Okay. Well, 5 is going to call Actually, I can probably do this. And there we go. So we want to add 3 to this tree. We're here in contain, so let's go ahead and move this up. So we're adding 3 to this, to over here. Is this null? No, it is not. So we call root.left. So we're adding 3 to the left subtree. And we're going to set the result as of that operation to our item. So we're not going to return this yet because we got to recurse into this own function. So now we're adding a 3 to 5's left subtree. And that ends up being null. So we're going to return. So we're going to create a new node and we're going to return it. Okay, notice I haven't drawn a line there yet. Now, back at the call of 5, at 5's call, right? 5 went, okay, I added 5 to, I did 5 here, and I got back this node 3, right? The node that contains 3, and I'm going to set that as root.left. And now I return root up here, and I say root is still the root, essentially. That's essentially all that does. Root is still the root. Why am I doing that? Because it makes it, again, a lot of this is happening for being symmetric with the remove method, which we'll go into, because that's actually going to take up a couple of videos rather than just one short one. Okay, now let's go into more detail. Let's go ahead and add 4. Okay, so we did 3. Okay, so now we add 4 to the tree, right? So we're adding this item. We're adding it to the tree that has 5 as its root. 5 is the root. 4 is the item. 5 is not null. 4 is less than 5, so we're going to add it to 5's left subtree. Then we go to 5's left subtree, which is 3. So we're adding 4 to the subtree with 3 in it. It's greater than, 3 is not null. We get back our comparison result. We compare 4 to 3, and we go, 4 is bigger than 3. So we're going to add it to 3's right subtree. What is 3's right subtree? Well, that turns out to be null. So we're going to return a new node containing 4. Whoops. New node containing 4. Okay. And now we're back in 3's call that it made to that. So here we're adding to 3's right subtree, and we got back a node with 4, and we're going to set that to our right subtree. Now 3 returns itself. And now we're back in over here in 5, and now we're back over here in 5's call, where basically it said add 4 to my left subtree, and we got back 3. So we set 3 to our left subtree, which doesn't actually change anything. And then we return root, which says, hey, keep the root still the root. Why do we make these calls if basically nothing changes? It's just so that the code is shorter and more elegant. It's much more, it makes a much more, marks the recursive call. It makes it much easier to see in that regard. It makes it, easier to read. And as you're going to see in the delete method, things can actually change quite a bit when we do this. And this just helps it keep it symmetric. And it just works. So we need to actually prove it works, though. So let me go over the toString method.